Now that we've had a look at several techniques for solving quadratic equations, we are going to look at how to graph quadratic equations. Now when you get to college algebra, you'll go into a lot more detail, not only looking at quadratic equations, but also any polynomial equation and how to graph it. For our class, we're just going to take a brief introduction to graphing quadratics, and we'll start by using a table of values. We've seen this technique when we were graphing lines before. We have a table of x values that we plug in. We'll then find y values that coordinate with them. And those ordered pairs will result in points on a graph that we can eventually connect. So let's take this example here where we have y equals x squared minus 4. And for the first row of my table where x is -3, I will plug in a -3 for x. And remember that whenever you plug something in, you should be putting parentheses around it. In this case, it makes a difference. What I'm squaring is not just the 3, but the entire -3. -3 times itself is positive 9, and 9 minus 4 will give me 5. So this is telling me that when x is -3, y is 5. That now corresponds to a point on a graph, -3, 5. We need several points to be able to get the graph of a quadratic equation, so let's keep going. Let's now plug in -2 for x. Y equals -2 squared minus 4. -2 squared is -2 times -2, which is 4, and 4 minus 4 will give us 0. So now when x is -2, y is 0, and we have now a second point. Now when it came to linear equations, 2 points was all we actually needed, because with 2 points I can connect them with a straight line, but this isn't a linear equation, it's a quadratic. My picture won't be a straight line, and so 2 points is not going to be enough this time. I'm going to want to fill out all 7 of these ordered pairs. So let's go on to the next one. Y equals x squared minus 4, now we're going to have -1 squared minus 4. -1 squared is -1 times -1, which is positive 1. And 1 minus 4 is -3. Now when we were working with lines, we happened at this point to notice a pattern that we continued to add or subtract the same value to go from one row to the next. The pattern here is not the same as with a linear. Here, to go from 5 to 0, I subtracted 5, but to go from 0 to -3, I only subtracted 3. So this is not constant like a line, it's going to be changing. So let's see what happens for the next. Let's now plug in 0. Y equals 0 squared minus 4. 0 squared is just 0. 0 minus 4 is -4. So this time, rather than going down by 5 or down by 3, I've only gone down by 1. So I'm actually slowing down here. Let's take a look at the next one where x is 1. Y equals 1 squared minus 4. 1 squared is 1, and 1 minus 4 is -3, and interestingly enough, this is now a repeat of a value we've seen before. So what we did was we jumped down 5, down 3, down 1, and we were slowing down. Now we're jumping back up 1. Let's see what happens in the next row. Now if I plug in x equals 2, I get 2 squared minus 4. 2 squared is 4, and 4 minus 4 is 0. That's another value that has repeated in the table. And based on the repetition we're seeing, from here, I see repetition, repetition. I'm going to take a guess that this next one's going to be a 5. Let's just see if that happens. Plugging in 3 for x. Let's see if we get y equals 5 as a mirror image here. So plugging in 3 for x, 3 squared minus 4. 3 squared is 9. 9 minus 4 is in fact 5. So where with the lines, we were able to recognize a pattern of add the same number over and over, or maybe subtract the same number over and over. The pattern here with the quadratics is that there's symmetry involved. If we look at this row right here, we notice that that row sort of acts like a mirror, where on either side of that mirror we see the same exact reflected y values. That mirror means something important when we go to the graph. So let's take this table of values and plot these 7 ordered pairs as points and see what that mirror looks like in the graph. So let's take these 7 ordered pairs we just calculated in our table of values and draw them as points on this graph. Remember that x values are the ones that go left and right, y values are the ones that go up and down. So for the ordered pair -3, 5, I will go left 3, up 5 to plot my point. So left 3 and up 5 would put me about here. The point -2, 0 says to go left 2, but don't go up or down, just left 2. So there's my second point. Again, this is not a linear equation, so this will not be a straight line. I cannot just connect these two with a straight line. Let's keep going and see what shape it does take. -1, -3 says to go left 1, down 3. That puts us about here. And then this was what we said kind of was like a mirror, where we saw a reflection of y values on either side of it. Let's see what this gives us. 0, -4 says don't go left or right, simply go down 4 and plot a point. And then after that we have 1, -3, which says go right 1, down 3. Then we have 2, 0, which says go right 2, but don't go up or down. And then we have 3, 5, which says go to the right 3 and up 5. And that puts us about there. So this is certainly not a straight line. This is actually a shape that we call a parabola. We saw this before when we were looking at an introduction to functions. And a parabola is kind of like a U shape. So something like that. Couple things that we want to note about this parabola shape. Number 1, let's talk about this mirror that we identified in our table. We were able to see that it was special in the table because on either side of this row, I saw repeated values, I saw reflected values. That point, 0, -4, is this point right here. It shows visually as the lowest or minimum point of this parabola shape. It's the lowest the graph gets. It has a special name. That point is called the vertex. And on some of your homework problems, you're going to be asked to find the vertex. The vertex is that mirror, which is 0, -4. The vertex will show in this example as the lowest value. Sometimes, like in the next example, we'll see it as the highest value. Here it's the lowest part of the valley. The other piece of information that we want to see is that this parabola should be roughly symmetric. It should have the same image over here as over there, just a reflected mirrored version. And we saw that in the table as well. We saw those reflected values. But there exists a piece of information in this graph that essentially says there is a mirrored reflected image, and that's what we call an axis of symmetry. If you imagine, in this case, the y-axis cutting through this picture, and if you were to take this as a piece of paper and fold it over that line, it's the same exact picture. It's a reflected image. And so this green dotted line here, it is dotted because it's not technically part of the graph, but that is called the axis of symmetry. It's essentially your mirror. Your axis of symmetry is always going to be some vertical line that cuts through the vertex, and a vertical line is described using an x equals. And at the vertex, the x values all along this line here, all the x values are the same as the x value in the vertex, which is 0. So you have your vertex, which is in this case the bottom of the valley. You saw it in your table as the mirrored part where the reflections happened outside of it. The axis of symmetry will always say x equals because it's always going to be a vertical line. It will always be the same x value as what's in your vertex. Let's take a look at another example. This time I'm going to have the parabola flipped over, so it's actually opening down instead of up. We'll see that the vertex, instead of being the bottom of the valley, it'll be the top of the hill. But let's do the table of values again, see if we capture that reflection, get the picture, and then find the vertex and the axis of symmetry again. So here's our second example of a quadratic equation that we'd like to graph. Again, I know this is quadratic because the highest exponent I see is 2. What I want to do to complete this table of values is plug in these various x values for every x that shows up in my equation. Now, I always like to start with these 7 values because it gives me negatives and positives that are relatively small. It also gives me 0, so it gives me a lot of different types of numbers. We may need to add to this. We'll see what happens. So I'm going to rewrite this equation, but where I see the x's, I'm going to replace them with -3. So I have negative x, which is -3 squared, plus 2 times x, which is -3 minus 1. Notice again, I'm putting parentheses around the x value I'm plugging in. And now we have to be really careful with our order of operations. I am not going to multiply the negative first. I have to deal with the exponent first. -3 squared is -3 times -3, which is 9. So I have the negative out front. -3 squared is 9. And now 2 times -3 is -6, and then I have -1. And if I combine all this together, -9 minus 6 is -15. -15 minus 1 is -16. Now I want you to imagine your graph. -16 is a pretty big number. It's pretty far down for y. I don't really think I'm going to like this number so much. So I think what I'm going to do is I'm going to cut -3 from my table. I don't think it's going to be helpful because I don't want to have to deal with numbers that are that big. I'm willing to go up to 10, but not past 10. So let's maybe cut that one, and I won't use it in my graph. So it's a true statement, the row is fine, but I probably won't be able to use it in my graph because it's too big of a number. Let's go to the next row and see what we've got. Y equals, again plugging in x, this time -2, I have negative x squared plus 2 times x minus 1. So every time I said x, I just plugged in a -2. Again, remember that you have to square before you're allowed to multiply. So I'm going to copy that negative coefficient, but I'm going to square this -2. -2 squared is -2 times -2, which is 4. So the negative is still there, -2 squared is 4. And now 2 times -2 is -4, and then I have -1. And here, -4 minus 4 is -8, -8 minus 1 is -9. Since that's less than the 10, I'll go ahead and keep that one. That one should be good enough for my picture. Okay, now keep in mind as we're going through this, at some point we're going to see a mirror image. I don't see anything yet, so let's keep going. This time let's plug in -1. Everywhere I see x, so negative x squared plus 2 times x minus 1. Everywhere I saw an x, I wrote parentheses -1. So now again, exponent before you multiply. So I have the negative out front, but the -1 squared is just 1. 2 times -1 is -2, and then minus 1. -1 minus 2 is -3. -3 minus 1 is -4. And that's a nice enough number. I'm going to keep that one as well. I don't see any mirror image yet, so I'm just going to keep going. This time plugging in 0. Negative x squared plus 2 times x minus 1. Again, I want to square before I negate. So 0 squared is 0. If I have a negative in front of that 0, it's not going to make a difference. And then 2 times 0 is 0, and then minus 1. So -0 plus 0 is 0. 0 minus 1 is -1. I still don't see any kind of a pattern or reflection, so I need to keep going. This time I'm plugging in x is 1. y equals negative x squared plus 2 times x minus 1. This time everywhere I saw the x, I put a 1. And again, I'm squaring before I multiply by that negative. So I have a negative that I copy, and then when I square 1, I get 1. Now 2 times 1 is 2, and then I copy the minus 1. Negative 1 plus 2 is 1. 1 minus 1 is 0. Still don't see any pattern. At some point, I sure hope we do, because a parabola should start having a mirror image at some point. Let's now try x equals 2. Again, plugging into the original equation, negative x squared plus 2 times x minus 1. This time x is 2. Again, square before you multiply. 2 squared is 4, so I have negative in front and then a 4. 2 times 2 is also 4, and then I copy my minus 1. So negative 4 plus 4 is 0. 0 minus 1 is negative 1. And finally, I see some repetition. So from there, we can identify where the mirror is going to be located. The mirror will be right here. On either side of that mirror, we're going to find reflections. So without even doing any computations, I can tell right now this number is going to be negative 4, simply based on that mirroring effect. And if I want, I can add this extra row down here to show the mirror image of negative 9 based on the pattern that I have in my left column. 1, 2, 3, my x value that would go with that is 4. So now I've got really 8 points, but one of them's too big, I won't put it in my graph. I now have these 7 points I'm going to go ahead and add to my graph, see if I get that parabola shape. I want to see if it's opening down, because the leading negative should make parabolas open downward. And let's see if we can identify this mirror as a vertex as well as the axis of symmetry. So again, once we've completed our table of values, we can transform these ordered pairs into points on a graph. Again, the negative 16 was just so low on the y-axis that I'm not going to want to include it in my table, but I still have 7 other ordered pairs that will work nicely. Let's begin with the negative 2, negative 9, which says to go left 2, down 9. We'll plot a point. Next we have negative 1, negative 4. I'm going to go left 1, down 4. Then we have 0, negative 1, which says don't go left or right, simply go down 1. And then I have 1, 0, which says go right 1, but don't go up or down. I'm starting to see it curve a little bit. Now that 1, 0 we just plotted was supposed to be the mirror based on what we saw on the table, so let's see if that becomes the vertex. Next is 2, negative 1, so I go right 2, down 1. It looks like that is going to be the top of the hill here, so that is the vertex. Next I have 3, negative 4, so right 3, down 4. And last I have 4, negative 9, which says go right 4 and down 9. And so again, I'm seeing that parabola shape. This time it's opening down. The difference is because here my leading coefficient was negative. But when I connect these dots, I'm getting that parabola shape. The vertex, in this case, is the top of the hill, not the bottom of the valley anymore, because it's opening a different direction, but it's still that point we were able to identify in the table. So there's our vertex, which you can get either from the picture or from the table. The vertex is 1, 0. We went right 1, but didn't go up or down. Then the other piece of information that we want is that axis of symmetry, which is just saying basically where's the mirror or the line that cuts through this and creates that mirror image or symmetric picture on either side. And in this case, it's where x is 1. I have a vertical line I can draw through this. There's my mirror. And so the axis of symmetry we can describe as the line x equals 1. So the vertex will always be written as a point or an ordered pair, x, y. The axis of symmetry will always be written as a line, x equals whatever the x value was in the vertex. So in this case, it's x equals 1 because 1 was the x value in the vertex, and that's where the axis of symmetry cuts through. Let's try a couple more examples to get some extra practice. Okay, again, so as we begin to fill in our table of values, our job is to plug and chug. Again, I'm starting with these same 7 values as I usually start with because it gives me some negatives, some positives, and a 0. But as we saw in the last example, sometimes we have to modify that. So let's see if we need to or not. We'll begin by plugging and chugging. We'll start with our equation y equals, and then everywhere I see an x, I'll use parentheses around the value I plug in. So we have x squared, in this case that's negative 3 in parentheses, squared, plus 4 times x, so 4 times negative 3 in parentheses, and then plus 2. So here we have negative 3 squared, which is negative 3 times negative 3, that gives us 9. Here we have 4 times negative 3, which is negative 12. And then we have plus 2. 9 minus 12 would give me negative 3. Negative 3 plus 2 is negative 1. So there's my y value when x is negative 3. We're going to continue going through the table until we see where the mirror is. If we can find the mirror, we can go ahead and reflect all of the other values. So now we're plugging in negative 2. Again, x squared, this time it's negative 2 squared, plus 4x, so plus 4 times negative 2, and then plus 2. Negative 2 squared is negative 2 times negative 2, which is 4. 4 times negative 2 is negative 8, and then we have plus 2. 4 minus 8 is negative 4. Negative 4 plus 2 gives us negative 2. I don't see at this point any ability to see a mirror. I only have 2 values, so I can't see any reflections yet. Let's keep going. Now we have y equals negative 1 squared plus 4 times negative 1 plus 2. Negative 1 squared will give us positive 1. 4 times negative 1 is minus 4. And then we have plus 2. So 1 minus 4 is negative 3. Negative 3 plus 2 is negative 1. Now, interestingly enough, I already can see the mirror. I have now a y value that has been repeated, and it's reflecting over a mirror that I can now see at negative 2 comma negative 2. So here's the deal. That's enough information for me to know where the vertex is, but 3 points is not enough to get a good picture of a quadratic equation. I can't see a parabola from just 3 points. If I had only 3 points, it would look kind of like a V instead of a curvier U. So I need to get some additional points down here. Now, if I can get some additional calculations here, remember I can do a mirror image for the other side. So I only need one side of that mirror to keep going. Let's now check out 0. Y equals, again, x squared, so here that's 0 squared. Plus 4 times x is 4 times 0, plus 2. 0 squared is 0, 4 times 0 is 0, and then plus 2. 0 plus 0 plus 2 is just 2. So I know if 0 is going to give me 2, that 2 will be reflected where x was negative 4 as well. We can deal with that when we get to the graph. We don't necessarily have to add it to this table. But let's keep going. We eventually want to have 7 points for our picture. Right now I have 1, 2, 3, 4, plus this guy's reflection. I have 5 points. I want at least 2 more. Here we go. Let's plug in a 1. So 1 squared plus 4 times 1 plus 2. 1 squared gives me 1. 4 times 1 gives me 4. And then I add 2. So here I have 1 plus 4, which is 5. 5 plus 2 is 7. Keep in mind that when I find this 7, there will be a mirror image of that 7 on the other end. Let's just make sure that we've got all the numbers we're going to want. If I continue and try x being 2, let's see what happens. If I plug in 2 for x, 2 squared gives me 4. 4 times 2 gives me 8. And then I'm adding 2. Now 4 plus 8 is 12. 12 plus 2 is 14. That number's too large. So while I can use it in my table, I'm not going to want to graph with that number because really once I get past the tens, my graph is too big. So I'm going to go ahead and cut it off here. And while I only see 5 pairs here, remember these two have mirror images on the other side that I can also use. So there are really 2 additional, so there really still are 7 ordered pairs. Let's get those 7 ordered pairs on a graph and make sure it's looking like a parabola. Okay, so let's plot the 5 points we have in our table and see if we can gather the additional 2 from the symmetry. So the first point in my table is the -3, -1. So that tells me to go left 3, down 1. And so there's the first point from the table. The next point is -2, -2, which says to go left 2, down 2. After that, we have -1, -1, which says go left 1, down 1. And so now you can tell here's where the parabola curves around. It had a positive leading coefficient, so it is going to open up. There's my bottom of my valley, that's my vertex. Let's see how it continues. 0, 2 says don't go left or right, simply go up 2. And then 1, 7 says to go right 1 and up 7. So I've got a good chunk of the parabola done, but to add that extra accuracy, I do want to take the mirror image of these additional 2 points I had at that lower end of my table that I could have used up there. So here where I had a height of 2, I'm going to scoot over and capture that same height of 2 on the other side. Here where I had the height of 7, I'm going to do the same thing, capturing it on the other side. Now you could certainly add those rows to your table to see the actual values, or you could just do it visually, it's up to you. But once you have all 7 points, then you can go ahead and connect the dots with this curve. And then the pieces of information that we want to gather from the picture, number 1, we want to see the vertex. We know that the vertex is either the bottom of the valley or the tip of the hill. In this case, it's the bottom of the valley. It's the same place that we identified as the mirror in our table. In this case, the vertex is -2, -2. So you can certainly pull that from the table, or you can see it visually in your graph. The other piece of information we want to gather is the axis of symmetry. Again, the axis of symmetry will always be the vertical line that cuts through the parabola at the point where it would show a mirror image. And the axis of symmetry, go ahead and write it over here, the axis of symmetry will always be written as an equation, x equals whatever the x value was from the vertex, in this case -2. So your vertex you can see either in your table or in your graph. Your axis of symmetry will always say x equals whatever this x value is. It's the vertical dotted line that cuts through your parabola. Let's take a look at one more. This next one will also open down as did the previous one. Again, it opens down if it has a negative in front. It opens up when it's a positive leading coefficient. Let's take a look at just this one more. So just one more time, again, as we fill in a table of values, it's all about plugging and chugging. I will again begin with my same 7 values that I like to begin with. If I need to adjust that down the road, I will. But let's begin by plugging in -3. So y equals negative, x squared will be -3 squared. Again, notice the negative exists and then the x turned into the parentheses around the value. So make sure you're using parentheses when you plug something in. Plus 6 times x, so that's 6 times -3 in parentheses, minus 13. Again, remember we have to square before we can multiply. So the negative just gets copied, and then -3 squared is -3 times -3, which is 9. And then 6 times -3 is -18. Then we have minus 13. And good golly, this is not going to be good news. -9 minus 18 is -27. -27 minus 13. That's going to be way too big. I don't even want to talk about that one. Let's just not even talk about it. That one's going to be cut. And you know what? If that one's so far off from 10, my guess is some of these are going to be pretty big as well. So I'm going to actually jump the gun here. So this was, what, 27? This was negative 40. Negative 40 is way too far out there. So I'm going to actually jump quite a bit to the 0, just to try it out and see how reasonable 0 would be to graph. Negative 40 is way too low. Let's try the 0. So negative x squared plus 6 times 0 minus 13. Let's give this one a try. 0 squared is 0. So I've got the negative 0. And then 6 times 0 is 0. And then I have minus 13. 0 plus 0 minus 13 is negative 13. I did get bigger. I went from negative 40 up to negative 13, but this is still too small. So it's telling me all this stuff is way too negative, way too much. I don't want any of that stuff. Let's keep going. Let's see if maybe the 1 will work. Negative x squared plus 6 times x minus 13. Let's see how this one goes. We have negative 1 squared, so that's negative 1. 6 times 1 is 6, and then we have minus 13. So negative 1 plus 6 is 5. 5 minus 13 is negative 8. Thank goodness that's something that I'm willing to graph. So when x is 1, y is negative 8. That's the first value I'm even willing to look at, so I'm glad that I've got something there. Now here's the deal. I know I'm going to run out of room. I have not enough room to put all my things here. So here's what I'm going to do. I'm actually going to rewrite this table now. None of those values, negative 3 through 0, were helpful whatsoever. I'm actually going to reorder this. So I'm going to start with 1, which I now know gives me a number I can work with. And then from 1, I'm going to continue. So 1, 2, 3, 4, 5, 6, 7. I still want 7 values. I said that when x was 1, y was negative 8, so I'm going to go ahead and move that up to this top row now. Just leaving myself room, because I know I'm going to need room for 7 values. I did not have room before. So let me get some more space here. So I already had my work to prove that one. Let's now work on x is 2. Y equals negative x squared, so that's going to be negative 2 squared plus 6 times 2 minus 13. So again, remember exponents before you multiply. So 2 squared is 4, so this gives me negative 4. And then 6 times 2 will be 12, and then minus 13. So negative 4 plus 12 is going to give me 8. 8 minus 13 is negative 5. That's again a number I'm willing to graph. It's not ginormous like the others were. So we're in good shape. We're on the right track now. So again, you know, it doesn't matter what you choose for x's, but I would just say if when you start plugging things in, you find that you have y values that are just outrageously too large to be able to fit in a graph that you're willing to graph, cut them. You don't need them. You get to pick what x's you want. And so my standard negative 3, negative 2, negative 1, 0, 1, 2, 3, that wasn't going to work here. I had to adjust until I found a number that was small enough for me to be willing to consider it. Now I have just a new set of x values. X is independent. You can pick whatever you want. Just pick something that'll fit in a graph nicely. So this time let's plug in a 3. Again, negative x squared. So here negative 3 squared plus 6x minus 13. Again, exponent before you multiply. 3 squared is 9, so this shows a negative in front of that 9. And now 6 times 3 is 18, and then minus 13. So now negative 9 plus 18 is 9. 9 minus 13 is negative 4. I don't see a mirror yet. I'm hoping it's coming soon. Let's see what we have in the next row. This time plugging in x equals 4. Negative x squared. So we have negative 4 squared plus 6 times 4 minus 13. Again, exponent before multiply. 4 squared is 16, so I'll have a negative in front of that 16. 6 times 4 is 24. and then I have the minus 13. So negative 16 plus 24 gives me 8. 8 minus 13 is negative 5. Now I see a mirror. I see the negative 5 repeats itself. So there is my mirror. And I'm going to go ahead and use the mirror to my advantage. I'm going to copy this negative 8. Now here's the deal. The value we had for 0 was negative 13. It was too far off the grid for me to want to include it. This value, when I plug in x is 6, would also give me negative 13. I just don't want to graph it. So in this case, unfortunately, I only have 5 ordered pairs, and so 5 points to work from. But it's going to be enough to get the picture. Let's take a look. Okay, so now taking our ordered pairs and translating them into points on the graph. First I have 1 comma negative 8, which says to go right 1 and down 8. Then I have 2 negative 5, so we go right 2, down 5. 3 negative 4, right 3, down 4. And then here's where I now have the mirror image. 4 negative 5 says to go right 4, down 5. And 5 negative 8 goes right 5, down 8. So I can see that the additional points I would have been quite low. That's where I would have had the negative 13s. And then if I really wanted to go all the way out to x equals negative 3, that's where I had that negative 40. It would be way down there. But this is enough to get the idea of the picture. There's my parabola shape. This time it's opening down, and that's because we had a leading coefficient that was negative. I can identify the vertex. In this case, it's the top of the hill here. The vertex, which we also saw in the table, the vertex was the point 3 comma negative 4. Remember, your vertex is always written as an ordered pair, x comma y. And then your axis of symmetry is going to be that vertical line that cuts through the center of that parabola. It's going to always be written, it's always going to be written as an equation, x equals whatever the x value was from your vertex, so in this case, 3. All right, so we've seen several examples now where we're just using the plug and chug technique for the table of values to get some ordered pairs, graph them as points, and connect the dots. Now when you are connecting the dots on your parabola, make sure it's not a harsh, sharp V. Make sure it curves a little bit at the top, or on an upward opening parabola, it curves at the bottom. It should be curvy, not sharp like a V. In the next video, what we'll be looking at is some different kinds of patterns that maybe we can recognize that are called transformations of graphs, which is something that you'll go into a lot more detail in with college algebra, but it'll be a lot more efficient than trying to plug and chug all of these different points.